Hello and welcome to this video on diagonalization. So this video is piggybacking off of my last video called Similar Matrices and Linear Transformations. If you want to take a look at that take a look at that. At the end of that last video on similar matrices and linear transformations, the very last example, we saw a linear operator, an example of a linear operator between two vector spaces, the same, where the domain and codomain were the same, and we looked at a basis, a specific basis for that domain and codomain, such that the matrix representation with respect to that basis was a diagonal matrix. And then this big question arose, which I have the same page. This is the same page as from the end of my last video right here. And I asked a big question that leads me into this video. I didn't have this word here last time, but this is called basically the diagonalization problem, or the question of diagonalization. So suppose we're given a linear operator, right? So some linear transformation from a vector space V into that same vector space. The question is there a basis B of this vector space V such that the matrix representation of T with respect to B is a diagonal matrix? And then I stated, this is equivalent to asking the following question. Given a square matrix A, right, because remember, every linear transformation, every linear operator can be represented by a standard matrix, a square matrix A. So given a square matrix A, that would represent some linear operator, is there an invertible, there's a V in there, sorry, is there an invertible matrix P such that P inverse times A times P is equal to D, where D is diagonal? And we're going to see the answer to that question today. Alright, so in this video we're going to see when does this happen. Alright, and I kind of gave you a hint in the end of that last video on similar matrices and linear transformations. It has a lot to do with the eigenvectors of A. Alright, it has a lot to do with the eigenvectors of A and whether or not you have enough linearly independent eigenvectors, and we'll get into that in this video here. So what I'm going to do is get into the diagonalization question, when we can answer yes, when we can answer no to this question. And then if the answer is yes, how do we find this matrix P such that this happens? P inverse times A times P equals a diagonal. Or, A equals P times D times P inverse. If you were to manipulate this, multiply it on the left by P and on the right by P inverse on both sides. Okay. And why the fascination with diagonal matrices also? And I have this page up on my last video as well. The reason we're interested in diagonalizing a square matrix or diagonalizing the standard matrix of some linear operator is because working with diagonal matrices is incredibly simple and very, very nice. So I would say, me personally, right, depending on your definition of nice, it might be different for you, but I would say diagonal matrices are the, quote-unquote nicest square matrices. So suppose, and let me just show you some properties of diagonal matrices here real quick before we get into the diagonalization of a square matrix problem. So suppose D equals, an n by n diagonal matrix. Remember, a diagonal matrix has, the only entries that could possibly be non-zero are down the main diagonal. So D11, D22, all the way to DNN, right, the nth row, nth column. And then so some of these could be 0, but if there are any non-zero entries, it could only be one of these. And then any entry off the main diagonal is 0. There's zeros all above, zeros all below the main diagonal in a diagonal matrix. Alright, so the beautiful thing, some nice things about a diagonal matrix is it's very easy to find the determinant of a diagonal matrix, right? It's just the product of the main diagonal entries, d11 times d22, all the way up to times dnn. And if all of these are non-zero, right, if all the entries are non-zero down the main diagonal, then the determinant won't be 0, and you can find the inverse. And the inverse of a diagonal matrix is another diagonal matrix, which is very simple. If you know what the main diagonal entries of the original matrix are, the main diagonal entries of its inverse are simply the reciprocals, right, or the multiplicative inverses of these main diagonals. So 1 over d11, 1 over d22, all the way down to the nth row, nth column, 1 over dnn. And again, every entry off the main diagonal is a 0. D transpose, if you were to switch rows with columns here, make each row into a column, each column into a row, take the transpose of D, you're getting D again. Right? The transpose of a diagonal matrix is that same matrix again. When this happens, when a matrix is equal to its own transpose, they call that matrix a symmetric matrix. So every diagonal matrix is a symmetric matrix. And here's a nice one too. All right, when you raise a diagonal matrix to some power, some integer power, so say d to the k power, your result, the resulting product, say it was d squared, d times d, the result would be the main diagonal entries of the original, to that power. So it's still another diagonal matrix, but you have d11 to the kth power, d22 to the kth power, all the way to dnn to the kth power, and then everywhere else off the main diagonal is a 0. Right, so like I said, if you squared a diagonal matrix, it's all the entries down the main diagonal get squared. You cube it, all the entries down the main diagonal are cubed, and so on. Very, very nice way to apply a matrix many, many times in a row. And when you multiply when you raise a matrix to powers like this, that's the same thing as applying a transformation that this is the matrix for, the matrix representation for, that many times, right? Or composing a transformation with itself that many times. And finally, the spectrum. We saw this before as well too. Remember the spectrum of a triangular matrix, and this, a diagonal matrix is definitely upper. It's both upper and lower triangular. Okay, a triangular matrix has the entries down the main diagonal were the eigenvalues of that matrix. So the spectrum, right, of a diagonal matrix is just the set with the main diagonal entries, d11 to dnn. Okay. So now we've talked about diagonal matrices and why they're so nice and why we would like to, if we can, take a square matrix A and kind of find a way to translate it into a diagonal matrix. Let's get into that process now. All right. So diagonalization is the process of finding that invertible matrix P and a diagonal matrix D such that, and this is what I had up earlier, the P inverse times A times P equals D, or again, like I said earlier, multiplying on the left by P and on the right by P inverse on both sides, A equals P times D times P inverse. Now, if this is happening, right, that means, and again, we talked about similar matrices in previous videos of mine. If you've been following, I hope you have, or in previous lessons that you've been reading, whatever. I'm hoping you remember what similar matrices are, because if this is happening, if you can find this invertible matrix P such that this happens, that means that matrix A and matrix D, this diagonal matrix, are similar. Right? They're similar matrices. And I'll get into this in a future video. Remember similar matrices. I've talked about these properties in the past, properties of similar matrices. Remember, similar matrices have the same determinant. They're either both invertible or both not invertible. They'll have the same rank, same nullity, the same eigenvalues, right? The same spectra. Lots of stuff. Lots of properties in the relationship between two similar matrices. So, and then a matrix A, so some square matrix A that is similar to a diagonal matrix like this is called diagonalizable. All right, so lots of long fancy words here. Diagonalization. A matrix is diagonalizable if it is similar to a diagonal matrix. And we say that this matrix P that we find, this P and P inverse, we say that the matrix P diagonalizes matrix A into matrix D. And that would be like this over here, this right equation, because I could multiply A by P and its inverse to make it into a to transform it, I guess, into a diagonal matrix. So we say that the matrix P diagonalizes matrix A into matrix D. Okay, so again, lots of fancy words involving the word diagonal there. But just keep this stuff in mind. All right. So next, I'm going to get into a very important result, something I hinted at in the last video, in the very last example. When can we diagonalize a matrix? When can we actually perform this diagonalization? When can we find this invertible matrix P such that these things happen? And with A and D being a matrix and a diagonal matrix. Now again, most of my videos, and maybe in the future I'll go over videos where I prove these things. The point of this video isn't to go through proofs. I'm just going to make some statements and we'll go through several examples. So this is the Diagonalization Theorem. Alright, so part 1. An n by n matrix A is diagonalizable if and only if. Remember, this means it goes in both directions. If this, then this, or if this, then this. Going backwards. Doing the converse. If and only if A has n linearly independent eigenvectors, right, which I'll call v1, v2, v1 through vn, vector 1 through vector n. Again, I'm assuming here you know what eigenvectors of a matrix are, right? If not, please go and find other videos, either of mine or someone else's, or read something in a book about what an eigenvector of a matrix is. Okay. So there's the answer to the question. When can I do this? Right? When can I diagonalize a matrix? The answer is when that matrix has n linearly independent eigenvectors, right? So if we're talking about a 2 by 2 matrix, it's only diagonalizable if the matrix has 2 linearly independent eigenvectors. If it's a 3 by 3, the matrix has to have 3 linearly independent eigenvectors. 4 by 4, 4, and so on. Right? Can't have fewer. Right? And it definitely can't have more. Right? But it can't have fewer than n. It has to have exactly n linearly independent eigenvectors if it's an n by n matrix in order to be able to be diagonalized. Right? And then here's how, right? This next part of the statement basically gives us how do we do this? How do we find this matrix P that diagonalizes matrix A into a diagonal matrix D? So again, if n by n matrix A is diagonalizable, right? So if you've determined this, and we'll see how to do that with some examples coming up, and has eigenpairs. Remember what an eigenpair is. I'm assuming that also. Lambda 1, and then it's eigenvalue with a corresponding eigenvector. Lambda 1 v1, lambda 2 v2, all the way to lambda n and vn. Again, where I'm saying that v1, v2, all the way to vn are these guys here, these linearly independent eigenvectors. Then you can find some matrix P in a diagonal matrix D such that A is equal to P times D times P inverse, or P inverse times A times P equals D, like the other equation I had written, right? Just manipulating this one. So here's how P is constructed, all right? Here's how we find this P. P is simply the matrix where each column of the matrix is one of these n independent eigenvectors. So you see the matrix notation here, the little brackets, and then column 1 is v1, column 2 is v2, column n is vn. So it's really that easy, right? But again, that's only if the matrix is diagonalizable, right? If you actually have n, if it's an n by n matrix, if you actually have n independent eigenvectors, then you can do this. You can construct this matrix. And the beautiful thing is, when you do this, as you saw in the, if you were watching, right, in the last example from that last video on similar matrices and linear transformations that I put up, when you construct a matrix like this, or have a base, this was like if those vectors formed a basis for the domain and codomain of some linear operator, the resulting matrix representation was this diagonal matrix where down the main diagonal are the eigenvalues of the matrix A. And they're going to come in the same order down the main diagonal from the upper left to lower right as the order that you put the eigenvectors in your matrix P. Right? So if I put v1 first and v1 was paired with lambda 1, then lambda 1 will be the first eigenvalue I see in the upper left corner of this diagonal matrix. And then v2, right, was paired with lambda 2. So if I put v2 second, then the second main diagonal entry will be lambda 2, and so on. Vn last, lambda n in the lower right corner. Lambda n is the last main diagonal entry in this diagonal matrix D. All right, but this is the crux right here. This is the important part. If it's diagonalizable and you can find eigenvalues and eigenvectors and find n linearly independent eigenvectors, this matrix P that diagonalizes matrix A into a diagonal matrix D, the way you make it is by simply making a matrix where the columns are these n independent eigenvectors. Okay, so examples. Now it's example time. So I've got a couple 2x2s, a couple 3x3s, and taking up the rest of the time. All right. So for each example, I have the same instructions. All right. I'm going to be asked. I'm asking first, determine if matrix A is diagonalizable. Right? Does it have? Would it have n independent eigenvectors? If so, then the matrix. Then find. I should say find. I didn't put the find. Right, then find the matrix P that diagonalizes A into a diagonal matrix D. Okay. So here I have matrix A it's a 2x2, right? So again, in order to be diagonalizable, we must be able to find two. Again, it's a 2 by 2 matrix. We must be able to find two independent, linearly independent, right? Independent eigenvectors of A. Right, and that's, that was part one of that diagonalization theorem. Alright, so what you're going to see in this video is something you've seen me do several times in other videos, but you might as well do it again. It can't hurt to see it again. Refresher, repetition is, helps you learn it. So the first part is I'm going to find these, find these eigenvalues and eigenvectors of A. All right. So one, find the eigenvalues of the matrix. All right. And hopefully you recall how to do this, right? This was, solve that what's called the characteristic equation for matrix A. That was, when is the determinant of the matrix A minus lambda I, right, where I was the in this case 2 by 2 identity matrix. When was that equal to 0? Right, you're solving this for lambda, right, finding different values of lambda that make this true. All right, so the determinant symbol, big bar around the matrix, and then what is A minus lambda I? Remember, it's just simply subtracting lambda from the main diagonal entries. So I have -2 minus lambda in the first row, first column, and again -2 minus lambda in the second row, second column, and then big bar again, for the determinant symbol. And then the other entries not on the main diagonal remain the same. All right, and let's see. This will give me what's called, the characteristic polynomial, and we're going to determine when that's equal to 0. So I have, remember 2 by 2s are easy, just cross minus cross here, right, a little cross product minus cross product. So -2 minus lambda multiplied by -2 minus lambda minus, 3 times 3, so 9. And I'll simplify this, multiplying these two, I'd have the negative lambdas together, it'd be positive lambda squared. Then I'd have plus 2 lambda plus another 2 lambda, it's plus 4 lambda. And then you'd have -2 times -2 as well, that's positive 4. But then minus 9 over here. You'd have positive 4 minus 9, minus 5. And this is very easily factorable. Now, if it weren't factorable, I'd just use the quadratic formula, because I'm going to eventually be setting this thing equal to 0 in solving. But this is nice and factorable. This is lambda plus 5 multiplied by lambda minus 1. Right? And again, the big question is, when is this equal to 0? And I have a very simple equation here, right? This is, a product on one side, 0 on the other. The only time a product will be equal to 0 is if one of the factors is 0. So when is this factor of lambda plus 5 equals 0? That would be when lambda is -5, right? And when is lambda minus 1? That factor 0. When lambda equals 1. All right. So the spectrum of matrix A, right, the set of all the eigenvalues, is the set with the numbers, -5 and positive 1 here. Now, I'll tell you right now, it's a 2 by 2 matrix, right? A is a 2 by 2 matrix. We have found two different eigenvalues. And remember, eigenvectors are, non-zero vectors, such that when you multiply A by those vectors, you get this number, this eigenvalue times that vector back, right? As an output. So remember, so each eigenvalue every distinct eigenvalue has an eigenspace associated with it. Remember, the eigenspace was the set of all the eigenvectors, and then also with the zero vector in there, but I'm focusing on the eigenvectors right now. And every eigenspace had an eigenbasis, right? Had an eigenbasis. And being that the zero vector is not an eigenvector, right? Every eigenbasis had at least one independent vector, right? At least one vector. So from the eigenbasis for the eigenspace corresponding to -5, I'm getting one eigenvector, at least, right? Well, it can't be higher than one itself. Remember, the dimension of an eigenspace is not going to be greater than the multiplicity of the eigenvalue in the characteristic equation. That was the geometric multiplicity was always less than or equal to the algebraic multiplicity. So we're getting one eigenvector from this, one eigenvector from that, and then another result that came up a while back was that if you take the union of the eigenbases of distinct eigenvalues, right, different eigenvalues, that union will be made up of independent vectors. So I do have two. I know I'll get two independent vectors if I go and find eigenvectors corresponding to -5 and -1. And that leads me to this thing here. I want to mention this also. Big result here. Big point out that's kind of demonstrated in this example. If an n by n matrix has n different or distinct eigenvalues, like this one has, right? This is a 2 by 2 with two distinct eigenvalues. Then that matrix will be diagonalizable. So again, if this is happening, then the matrix will be diagonalizable. Now, this is only going in one direction. Right? It's an if-then statement, not an if and only if statement. So if you see an n by n matrix with n distinct eigenvalues, like here, I have a 2 by 2 matrix with two distinct eigenvalues, then we know it's guaranteed that the matrix will be diagonalizable. However, just because this is true doesn't mean what's called the inverse, where I just negate these. That's not necessarily true. All right. So if an n by n matrix does not have n different eigenvalues, the matrix might be still diagonalizable. All right, and we're going to see an example of that coming up in this video, I promise you. All right. But if it doesn't have n different eigenvalues, then you kind of have to go further and check more to be able to answer the question. Is it diagonalizable or not? All right. So this has so this is a 2 by 2 matrix with two distinct, right, two different eigenvalues. So that tells me that A will be, or A is, diagonalizable. Okay. Now if that was the only question I was asked, I'd be done. But remember, the second part to this, my examples here, is going to be, okay, if it is, if I've determined that it is diagonalizable, then let's go and find that matrix that diagonalizes it. Find that invertible matrix P that diagonalizes A into a diagonal matrix D. All right, so remember, I said this on the previous page, this matrix P, its columns are simply made up of these eigenvectors, right? So now we have to find the eigenvectors. Right? I'm going to keep matrix A up there. So part 2, after finding the eigenvalues, find corresponding eigenvectors. All right, so I'll start off with, for lambda equals -5. The eigenvectors corresponding to lambda equals -5. Right. So remember how to find these, right? We're solving this equation, going back to a minus lambda I times some vectors x, right? And these vectors that solve the equation will be the eigenvectors, except for the 0 vector, of course. That's always a solution. When is this equal to the 0 vector, right? So we're solving the equation a plus 5i, right? If lambda is -5, this is a plus 5i times vector x equals 0. And what does the matrix A plus 5i look like? Well, it's just matrix A where I'm adding 5 to the main diagonal entries. If I do that, -2 plus 5 is 3, -2 plus 5 is 3. The matrix is made up of all 3's. So there's A plus 5i. And then, vector x, these vectors that solve this thing would have to have 2 components, say x1 and x2. And I'd like this to be equal to the 2 by 1 0 vector. And I could make an augmented matrix for this, write a system, but the column on the other side of the bar is going to be full of zeros, just a couple zeros, and that won't change when I go and put the matrix into reduced echelon form. So I'm just going to take the matrix A plus 5i and put this into reduced row echelon form, which is pretty simple, being it's only a 2 by 2, right? Obviously, if I take the -1 times the first row and add it to the second row will be all zeros, and then I just would multiply the first row by a third to get that leading 1. All right, so we see here that, looking at the pivots, x1 is basic, x2 is free, right? And again, you know me, I like to replace my free variables with other parameters that can take on any real number of values, so say x2 equals t. And then from that first row, remember there's an equal 0 on the other side. This is x1 plus x2, so plus t equals 0, meaning x1 is the opposite of x2, or the opposite of t. All right, so putting those together, I'm getting the solutions of that equation. This a plus 5i times x equals the 0 vector are, I can replace vector x with any vector that looks like this, where the first component, x1, is -t, and the second component is t, right, x2. Or just t times the vector -1, 1. Alright, so now again, this is infinitely many solutions here. I just need one. Right? I need a vector that would form a basis for the eigenspace. Remember this eigenspace of A corresponding to lambda equals -5, this notation. Alright, this was the eigenspace of A. That would just be the set of all these vectors here, the span of the set with the vector -1, 1 in it. Okay. So I'm just gonna take a basis vector, right? You could take any eigenvector from here, but I'm just going to take the one I see straight up, this -1, 1. Here's a basis vector, just the vector -1, 1. All right. So there's one, linearly independent eigenvector right now, and that came, that's corresponding to -5, and you can always double check, multiply matrix A here, right? Multiply matrix A by -1, 1. And your output should be 5, -5, right? It should be -5 times this. I'll also list the eigenpair, right? So that we're getting from here. So -5, comma, and then one of my basis for this space, -1, 1. Oops, I want to parentheses there, sorry. Right, so that is an eigenpair of A. Cool. All right, so keep that in mind. So what I'm going to do later, when I make this matrix P that I'm looking for, negative 1, 1, I'll make that my first column of matrix P. All right. Okay, so that was for negative 5. All right, then there was the other eigenvalue of 1. All right, so I'm going to do the same thing. Find an eigenvector corresponding to lambda equals 1. All right, so for lambda equals 1, all right, we're solving the equation a minus lambda I, so just a minus I, right? Lambda's 1 times some vector x, when is this equal to the 0 vector? And then what does a minus I look like? Just subtract 1 from the main diagonal entries, so I have negative 3 there, negative 3 there, and the other ones stay the same. My vector x will have two components, say x1 and x2. I'd like this to be equal to the 0 vector. And I'll put my my matrix here, the A minus I, into reduced echelon form or reduced row echelon form. Again, pretty simple, being that there's only 2 rows, right? It's obvious that if I just add the rows, the second row will be full of zeros, right? And then I would multiply the top row by negative 1/3, making this 1 and this negative 1. And then look at your pivot, right? So x1 is basic, first column has a pivot, second one doesn't. So I'm just gonna let x2 be equal t for where t is just any real number. Then from this first row, again imagining that there's an equal 0, we have x1 minus t equals 0. So adding t to both sides, I get x1 equals t as well. So the solutions here are just multiples of 1, 1, right? The coefficients of t here are 1 and 1. So the eigenspace of A corresponding to lambda equals 1 is just the span of the set with the vector 1, 1 in it. Right. And again, I'll just take this set with the vector 1, 1, right? And again, t times 1, t times 1. This set with the vector 1, 1 in it is a basis for this space, and I'm just going to use that vector as in my eigenpair. Again, I'm just using the basis vectors that I clearly see. You could use 2, 2, 3, 3 if you wanted. You can use any multiple of this, right? It's in the space, as long as it's not the 0 vector, right? The 0 vector is not an eigenvector. So I'm going to use this eigenpair, right? So 1, the eigenvalue of 1 with the vector 1, 1 is another eigenpair of matrix A, right? So I have found 2 independent eigenvectors, right? 2 eigenpairs. So yeah, negative 1, and you can very clearly see, remember the basis vectors for distinct eigenvalues are going to be independent. Right? I've mentioned that before. I've shown that. Well, I didn't go over a proof or anything, but again, I mentioned that result before. So 1, 1, negative 1, 1, right? These are independent. So I have taken this 2 by 2 matrix, and I have found 2 independent eigenvectors, negative 1, 1, and 1, 1. So it's definitely, as I mentioned earlier, it is definitely diagonalizable. And I'll show you one more time here. So, and here's how, right? So we have eigenpairs mentioned, right? Only 2 of them. Again, the matrix P that I'm looking for, the columns I'll just make with these eigenvectors. And what we're going to see is that when I multiply A by, say P inverse and P inverse on the left and P on the right, I'd get a diagonal matrix. And in fact, I'll just show that, right? So here's our diagonalizing matrix P. Right? So let's make our diagonalizing matrix P. I mean, I guess I should say a diagonalizing matrix, because You could put these eigenvectors in whatever order you wish. I mean, you just got to pay attention to what order you're putting them into. So it's going to be a 2 by 2. Right, where again, my first eigenvector I found, which was corresponding to -5, is -1, 1. So there's again, this is like that V1, right? My first independent, one of the two independent eigenvectors. And then the second eigenpair I found was this with one with the vector 1, 1. So the vector 1, 1 goes as my second column. Right? And again, I could have called this V2. Right, now be careful, right? Like I said earlier, this the order I put these in, I put this vector, right? Which this vector corresponded, the first column corresponded to the eigenvalue -5. The second column corresponds to eigenvalue 1. So now let's find this product. Right? Let's find P inverse times A times P. And what we're going to see is that this will be a diagonal matrix where down the main diagonal the numbers -5 and 1, those eigenvalues in the same order that I put the eigenvectors in will appear. Alright, well first I got to find P inverse then. Now again, this is a 2 by 2, so that shouldn't be too hard. Right? The determinant is -1 minus 1, so it's -2, meaning I take -1/2, and then times the adjoint matrix, right? Remember the reciprocal of the determinant times that adjoint matrix, which is the cofactor matrix transpose. Well, for a 2 by 2, that's just switching the main diagonal entries and then taking the opposites of the other entries. All right, so this should be the inverse, and if you want to multiply the whole thing by -1/2, be my guess, but I'm going to leave it like that. All right, so let's see what this is. So we have -1/2 times the matrix, 1, -1, -1, -1. There's P inverse. Matrix A is what we started with, right, with the -2, 3, and 3, -2. Times matrix P, which is the matrix that's made up of those, those independent eigenvectors as columns, -1, 1, and 1, 1. All right, and matrix multiplication is associative, so I'll just do these two first. So we have -1/2, and you can do this on your calculator if you wish, but just for this first example, I'm going to run through and do it by hand here. So a 2 by 2 times a 2 by 2 is going to be a 2 by 2. We've got 2 plus 3 is 5, and then -2 plus 3 is 1, and then -3 minus 2 is -5, and then 3 minus 2 is 1. Okay, and then multiplying these two matrices, so we got -1/2 out here still. First row, first column, 5 plus 5, 10. Then 1 minus 1, 0. -5 plus 5, 0. And then -1 plus -1, -2. And then multiplying each of these by that -1/2 out there. Look at this. -1/2 times 10, -5. And 0, 0. And then -1/2 times -2, +1. Look at that. That's the D. That's that diagonal that's a diagonal matrix, see? Down the main diagonal are these those only non-zero entries show up on the main diagonal, and there's zeros everywhere else. And look at these. These are the eigenvalues of A. These are the eigenvalues of A. Okay. And notice how the eigenvalues come in the same order that I put the eigenvectors. Remember this. Now, if you switch the order, you could. All right. If you switch the order, if I put 1, 1 first and then -1, 1, it would just switch the order of these values. So it's still doable. Right? It's still fine if you change the order. It's just going to change the order that the eigenvalues come in down the main diagonal of your diagonal matrix. That's all. And this is wonderful. All right, great. So A was diagonalizable, and here is the matrix. They would say that this matrix P, this matrix diagonalizes A into matrix D. Right. So we'd say that this matrix P diagonalizes A into matrix D because P inverse times A times P is diagonal. Right. Or A and D are similar, right? Okay, and as I'll mention in the next video, I come up with we'll have properties of diagonal matrices. Remember, A and D are similar, so they should have the same determinant. And remember, the determinant of D here is just -5. What's the determinant of A? 4 minus 9, -5. They should have the same. A and D here should have the same rank, the same nullity, the same eigenvalues, right? All the stuff involved with similar, regarding similar matrices will be happening with respect to this A and D here. Okay. Great. So again, you're really going through the same procedure you have been if you're probably working on this diagonalization after some section in your book, whatever you're looking at, on finding eigenvalues and eigenvectors. I can't see why you would see this stuff before finding eigenvalues and eigenvectors. So that's all you're really doing, is finding eigenvalues, finding corresponding eigenvectors, and if you find enough eigenvectors to where it's diagonalizable, then great. And if you don't, then it's not. All right, so here's another example. All right, again, a 2 by 2. All right, so this time, it's 2 by 2. It's an upper triangular matrix. All right, remember this is what they would call upper triangular. So I know the spectrum already. All right, remember, for an upper triangular or lower triangular or diagonal matrix, the eigenvalues were just the values down the main diagonal. So just 1, right? But it's repeated, right? So it has one distinct eigenvalue, right? There's only one distinct eigenvalue. And I guess you wouldn't really say it's distinct because there are technically 2 of them, right? Because, but really there's only one that's, there's only one eigenvalue. There's not 2, is all I'm saying. There are 2, but they're repeated. All right, so they're not 2 distinct eigenvalues. They're not 2 different eigenvalues. They're both the number 1. So remember earlier that doesn't mean that this matrix isn't diagonalizable. It just means I need to do more checking, right? If there were 2 eigenvalues, right? If I saw that there were 2 and it was a 2 by 2, then I would know right away that it's diagonalizable. But because there aren't 2 different eigenvalues here, A might be, right? I have to do more checking. I have to do more calculating. A might be, diagonalizable. All right. So it's just don't automatically say, oh no, And we're going to see an example also where there are some repeated, this is what they would call a repeated eigenvalue, right? There's 2 of them. We're going to see an example coming up where there is a repeated eigenvalue, but it's the matrix is still diagonalizable. This one unfortunately won't be. Let's check though, right? So so we have to check check for eigenvectors of the repeated eigenvalues first. right? Check for eigenvectors of the repeat eigenvalues first, I'll say. Right, because all the ones that show up once, right? All the eigenvalues that only show up one time, that only have a multiplicity of 1, you're going to get one eigenvector out of that. You know, the ones where the multiplicity is 2 or more, like this, you'll get at least one eigenvector out of that, but you don't know if you may get more than one. You know, you have to really check though. All right, so that's why I'm saying, like, don't worry about the ones that only repeat once. Don't worry about the ones that have a multiplicity of 1 for the moment. All right. Check for the ones that repeat. Check to see if there are enough eigenvectors coming from those, so that you'll have your n independent eigenvectors. All right. So for lambda equals 1. Again, I don't need to do the characteristic equation. I know lambda equals 1. We're finding eigenvectors, so I'm solving again this a minus lambda I, so just a minus I again, times vector x equals the 0 vector. A minus I is just 0, 0, 0, 2, like that, times some vector with two components, x1, x2, equal to the 0 vector. And wow, this is really easy to put into reduced, I mean, it's in echelon form already, but just reduced row echelon form. Multiply the top row by a half. All right. So 0, 1, 0, 0. So you see that, when you look at the pivots, pivots in the second column, so x2 is basic, but x1 is free. I'm going to let x1 be t, and then we see from this line here, again, you're imagining the equals 0 on the other side. x2 has to always be 0. So our solutions are t times 1, t times 0, I guess you could say, multiples of the vector 1, 0. And that's it, right? So the eigenspace of matrix A corresponding to lambda equals 1 is just the span of the set with the vector 1, 0. All right, it's all the eigenvectors are multiples of 1, 0, right, except for the 0 vector, right? I know the 0 vector's in here, but, again, eigenvectors are non-zero. So look, there's only one basis vector, right? This has dimension 1, right? So 1 has a geometric multiplicity of 1 and not 2, right? It has an algebraic multiplicity of 2, right? It repeats twice in that characteristic equation as a solution, but it only has a geometric multiplicity of 1. Yeah, so we're seeing here that, there's only one eigenvector coming from this, right? That vector 1, 0 that I'd be using. But it's a 2 by 2 matrix. And when I find all the basis vectors for the eigenvalues, right, I'm only finding one vector. That's not 2, right? I need to find 2. That was the statement earlier, right? A matrix is only, an n by n matrix is only is diagonalizable if and only if you can find n independent eigenvectors. All right, so that means we can't find 2 independent eigenvectors. Sorry. We can't find 2 independent eigenvectors. So therefore, this matrix A is not diagonalizable. All right. You cannot find a matrix P such that P inverse times A times P equals a diagonal matrix. You can't find it. You can't do it. It's impossible. All right. And great. But again, just be careful. Just because some eigenvalues repeat doesn't mean it might, it might be diagonalizable, it might not be, right? But you have to check those, right? And check to see that their geometric multiplicity is actually equal to the algebraic multiplicity, right? The dimension of the eigenspace is equal to the multiplicity, the number of times, the value is a solution in the characteristic equation. If they're equal, you're fine for all the repeating eigenvalues. But if there is a repeating eigenvalue out there where the geometric multiplicity is less than the algebraic multiplicity, like this one had a geometric multiplicity of 1, but an algebraic multiplicity of 2, then it's not diagonalizable, right? I guess that's another way you could put it. You can put a matrix is diagonalizable, if and only if each eigenvalue's geometric multiplicity equals their algebraic multiplicity. Okay, so you can think of it that way if you want. All right, next one. Now we're working up to our 3x3s. All right, I'm doing the same stuff, okay. So again, let's, now this one isn't diagonal, it's not triangular, not diagonal, so I can't tell what the eigenvalues are immediately, all right. So let's do it. All right, solve the characteristic equation. Let's try to find the eigenvalues, right? So when is the determinant of a minus lambda I equal to 0? So the determinant of, I got 1 minus lambda, 3 minus lambda, and negative 1 minus lambda down the main diagonal. And then, negative 1, 1 over here, and 1, negative 3, 1 over here. Okay. All right, so this time I'll do some cofactor expansion. All right, now let's go down the first row here. So we got 1 minus lambda multiplied by the minor, right? Get rid of that and that. 3, the 2 by 2 matrix left over. 3 minus lambda, 1, 1, negative 1 minus lambda. Okay, and then we're adding negative 1 times its cofactor. But remember the cofactor for an odd position. Right, this is first row, second column. 1 plus 2 is 3 is odd, right? Remember the cofactor for an odd position is just the opposite of the minor. So instead of adding negative 1 times the minor, the opposite of the minor, I'll just add 1 times the minor. So plus 1, or just the minor, plus 1, and then that minor, get rid of that and that. You have the 2 by 2 matrix 1, 1, negative 3, and negative 1 minus lambda. And then that one, then plus negative 1 times its cofactor, which will just be the minor, so we'll have minus 1. So minus this, this put minus 1, or just minus its minor, right? Get rid of that row and that column. You're left with this 2 by 2 matrix with 1, 3 minus lambda, negative 3, and 1. All right. So a little bit of algebra going on here, right? So we got 1 minus lambda multiplied by brackets here. I'm doing this determinant. We got 3 minus lambda multiplied by negative 1 minus lambda, and then minus 1. Okay, then we're adding to this, this determinant. So that's just negative 1 minus lambda, plus 3. All right, so that's easy to simplify there, and then minus, and then the quantity, this determinant, which will be 1, then minus negative 3 times 3 minus lambda, so plus 3, minus negative 3 plus 3 times 3 minus lambda. All right, we'll simplify that all here on the next page. So I've got 1 minus lambda. All right, and you know what? I'm just going to pause this for right now and get, come back when I get to the end of this. Okay, so I got a lot of writing down here, right? I started from here, multiplied all this out, and if you'd like to pause and see what happened, just be my guest. Take it all down here, factored this thing by grouping, ended up with this lambda minus 3 times 2 minus lambda times 2 plus lambda. Totally factored degree 3 polynomial, right? And then when is this equal to 0? Right, this equals 0 when lambda is equal to 3, right, for this first factor, or when lambda equals 2 for the second factor, or when lambda is equal to -2 for that third factor. All right. So the spectrum of matrix A here is the set with -2, +2, and +3. All right. So we said earlier, right? If you have a n by n matrix and it has n distinct eigenvalues, it's diagonalizable. This was a 3 by 3 matrix, and I see that it has three distinct eigenvalues. So A is going to be diagonalizable. All right, now that I know it's diagonalizable, right, then I should be able to go and finish it, right, actually diagonalize it, find the matrix that diagonalizes it, that invertible matrix P. So that'll involve finding, the eigenvectors corresponding to these, right, or at least, a eigenvector corresponding, right, a basis vector for the eigenspaces corresponding to these. All right, so we'll start with lambda equals -2. All right. So for lambda equals -2, again, really, I know I usually write out the equation and whatnot, but we're solving that equation, a minus lambda I times x equals 0, and it all boils down to just taking a minus lambda I and putting it into reduced echelon form, right, and then solving. So a minus lambda I here is a plus 2i. So I'm just going to focus on that, right? What does a plus 2i look like? It's just adding 2 to the main diagonal entry, so 3, and then 5, and then 1, and then all the other ones remain the same. And I'll actually go to the calculator this time and have this be put into reduced echelon form. All right, so go to the matrix menu, over to edit. Here's a 3 by 3. These entries, 3, -1, -1, 1, 5, 1, -3, 1, 1. Great. And just double check it, look it over, it's good. All right, get out of there. And back to the matrix, over to math, put in RREF, right? Reduced row echelon form, matrix A. And okay, so here we go into reduced row echelon form. This goes. We have 1, 0, 0, 0, 1, 0 columns, and then -1/4, +1/4, and 0. Okay, now again, don't forget you're imagining there's an equal 0 on the other side over there. So looking at the pivots, right, the first two columns are pivots, so say x1 and x2 are basic variables, and then x3 is free. So I'm going to let x3, now instead of t, remember when I had fractions in previous videos, just to get rid of those 4's there, right, the least common denominator of 4 and 4 is 4. I'm going to let x3, instead of be t, I'll have it be 4t. Right, that'll just get rid of these fourths, make them into 1t, -1t, and +1t. So up here I'd have x1 minus t, right, 1/4 of 4t equals 0. So adding t to both sides, x1 equals t. Here, x2 plus 1/4 of t, or just t, 1/4 of x3, sorry, 1/4 of x3, which is 1/4 of 4t, which would be just t. Have that equal 0, so I'd subtract t, get -t. And so you see I have t times 1, t times -1, t times 4. So 1, 1, 4, or sorry, 1, -1, 4 is a basis vector for the eigenspace, right? The eigenspace of A corresponding to lambda equals -2 is, any scalar multiple of the vector 1, -1, 4. All right. All right. And again, you can do t times this, where t is, anything but the 0 vector in here is an eigenvector, and you also have the 0 vector. All right. So I'll write out the eigenpair that we're going to be using. All right. So -2 and this vector, this basis vector 1, -1, 4. All right. We'll use that eigenpair. Okay. Wonderful. All right. Then for lambda equals, right, the other eigenvalues were 2 and 3, right? So that was -2 for lambda equals +2. Same thing. All right, so we're looking at a minus 2i, right? And again, I know there's times x equals 0, but like I said, just imagine it's there. Right? I've done a bunch of these. This is just subtracting 2 down the main diagonal, so 1 minus 2, -1, 3 minus 2, 1, -1 minus 2, -3. Then all the other entries remain the same. All right, and I'm going to have this be put into reduced row echelon form again. Now, again, the nice thing is, since I've already entered my last one, I just need to change. The only things that are changing are those main diagonal entries, right? So when I go back to the matrix menu over to editing, I'm just changing the main diagonal entries. So 3 becomes -1 here. Move it down to the middle. Second row, second column is 1 now. And then -3 for the third row, third column. All right, and I've already entered reduced row echelon form last time, so just second entry, just do it again. There we go. And we're getting this matrix with 1, 0, 0, 0, 1, 0, and 1, 0, 0. All right, so looking at the pivots, all right, those leading ones in the rows, there's a pivot in the first column, pivot in the second column. So again, third column, corresponds to that, say x3, the third component of the vector x I'm looking for. Call that t, that, there's no fractions here. Let's say x3 is t. And from the second row, we're seeing that x2 is always going to be equal to 0, right? Again, you're imagining the equal 0 on the other side. And then from the first row, we're seeing that x1 plus x3, so x1 plus t must be equal to 0. Subtracting t from both sides, you get x1 equals -t. So that's t times -1. X2 is t times 0, and x3 is t times 1. So -1, 0, 1 is a basis vector for the eigenspace, right? The eigenspace of A corresponding to +2 for lambda is going to be the span of the set with the vector, -1, 0, 1. All right, so I'll write I'll write our eigenpair that we're using here, +2 for the eigenvalue, and the eigenvector -1, 0, 1. All right, and then finally for the third one, lambda equals 3. All right, just doing the same stuff. All right, for lambda equals 3, we're looking at a minus 3i. Right, a minus lambda I, what does that matrix look like? And just subtracting 3 down the main diagonal, 1 minus 3, -2. 3 minus 3, 0, -1 minus 3, -4, and then everything else stays the same. Putting this into reduced row echelon form. Again, very easy to do on the calculator here, since all I need to change are the main diagonal entries. Alright, so that's -2 now. Then 0, and -4. Alright, getting out of here, re-entering reduced row echelon form, and there we have it. So 1, 0, 0, 0, 1, 0, 1, -1, 0. Alright, again, imagine the equals 0 on the other side. First column is a pivot column, second column is a pivot column, right? Again, the third column is representing, the coefficients of x3. Again, if I called my vector x1, x2, x3, that's a free variable. I'm going to let x3 be t again. seeing from the second row that x2 must be equal to t as well, because it's x2 minus t equals 0, add t. And then x1 must be the opposite of t, right? That's x1 plus t equals 0, subtract t. So t times negative 1, t times 1, t times 1. So negative 1, 1, 1 is a basis vector that I'll use from the eigenspace, right? The eigenspace of A corresponding to lambda equals 3 is the span of the set with the vector negative 1, 1, 1. All right, so the third eigenpair and that third independent eigenvector we're using is 3 and then negative 1, 1, 1. All right, parentheses, okay. So we have our 3 eigenpairs. All right, it's a 3 by 3 matrix, and I have found you 3 independent eigenvectors, right? Remember, these basis vectors for the eigenspaces of distinct eigenvalues should be independent. So 1, negative 1, 4 corresponds to negative 2. Then negative 1, 0, 1 corresponds to positive 2, and negative 1, 1, 1 corresponds to positive 3. So I should now be able to construct the diagonalizing matrix for matrix A. All right, that was that matrix P. All right, so here it is. So P equals, and again, the columns of P are simply these independent eigenvectors. All right, so from our first eigenpair, again, the vector 1, negative 1, 4. 1, negative 1, 4. Second column of P, the second vector from the second independent vector from our second eigenpair, that was negative 1, 0, 1. Negative 1, 0, 1. And then the third column, negative 1, 1, 1 from the value corresponding to eigenvalue 3. Now, this matrix should diagonalize. Right, this diagonalizes A into a diagonal matrix D. Right, now we can find out what D is by doing this, taking P inverse times A times P and seeing what we get. Now again, I'm just going to go to the calculator here and enter these matrices. All right, so let me show you. So back to the matrix. So again, back to edit here. The three, this is matrix A. I'll just make the diagonal entries back to what they were originally, right? So 1, then the second row, second column is a 3 again, and third row, third column is a negative 1 again. All right, then I go back to the matrix menu, over to edit again, and this matrix P, I'll just go to matrix B on the calculator because it doesn't go down to P. Okay, so I'll just go to matrix B and make another 3 by 3. With these entries, from matrix P here on my page. So first row, 1, negative 1, negative 1. Second row, negative 1, 0, 1. Third row, 4, 1, 1. All right, and then let's find this. Now again, it's called matrix B on my calculator, so I'm going to do B inverse times A times B, and what it should be, right? Because look, the order I put these columns in. Remember, this vector, the first column, this eigenvector corresponded to eigenvalue negative 2. The second column corresponded to eigenvalue positive 2, and the third column corresponded to eigenvalue positive 3. So the diagonal matrix I should get, the D here, should have negative 2, positive 2, and positive 3 in that order going down the main diagonal from the upper left to the lower right. And let's see that happen. Right, so matrix, I'm going to do matrix B inverse. Right, so B and then the little x to the negative 1 button here, times matrix A, and then times matrix B again. Well, not B again, but we did B inverse before, but times matrix B. And look at this, diagonal matrix diagonal matrix where, again, I mentioned it already, -2, +2, +3 down the main diagonal. And then, it is a diagonal matrix, right? Zeros everywhere else. And this is that matrix D that's being talked about up here when I say P diagonalizes A into D. Right? And like I said before, you can change the order of these as long as the column vectors are independent. Right? As long as there are enough of them to make a square matrix and all the column vectors are independent, this should work out. So if I switch, the first two here, if I put -1, if I put -1, 0, 1 first and then 1, -1, 4, it would just switch the order of these two. It would be 2, -2, then 3. Right? That's all that would change if I change the order in which the eigenvectors come. All right. Wonderful. All right. So I've got one final example. All right. And this time I'm going to kind of do a little more pausing and skipping ahead instead of writing out every single little thing. So here, matrix A, it's another 3 by 3. There's a lot of zeros in this one, so finding the determinants and stuff shouldn't be too tough, when you're trying to find the eigenvalues and whatnot. But yeah, so I see right away that the number 2, well, -2, right? If I subtract -2 from the main diagonal entries, I'm going to get a 0 here, and then you'll definitely have a matrix with a determinant 0. So I already see that -2 is going to be an eigenvalue. All right, so first of all, is it diagonalizable? So same thing, solving that. When is that characteristic equation? When is the determinant of a minus lambda I equal to 0? All right, and I will do the same thing I did last time. I'll set up the determinant page here, the picture here, and then pause it and just kind of do a little bit of writing and show you what the final result is. Find these eigenvalues. So subtract lambda down the main diagonal. 1 minus lambda, 1 minus lambda, -2 minus lambda. Actually I won't pause it. This is going to be a short one. Then 3, because again I mentioned there's lots of zeros here, so 3, 0, 0. And finding this determinant would be easy, right? Just go down, doing cofactor expansion down the third column or the third row. I'd have -2 minus lambda here, right? Times, and then I'll just do the determinant, the minor right now. So it'd be 1 minus lambda times 1 minus lambda, so 1 minus lambda, squared, minus 9. Okay, and got -2 minus lambda, which is already its own factor, right? -2 minus lambda. And then this here is a difference of squares. So this will factor to 1 minus lambda minus 3 times 1 minus lambda plus 3, right? Or you could actually multiply it out and get something that would be easily factorable as well. So I've got -2 minus lambda times, and then here, 1 minus lambda minus 3, that's -2 minus lambda again. Whoa. So you see I'm going to have a solution that's repeating. I'm going to have an eigenvalue with an algebraic multiplicity of 2. Hopefully the geometric multiplicity is also 2, right? The dimension of its eigenspace. And then 1 minus lambda plus 3, that's 4 minus lambda. Right? 1 plus 3 minus lambda. So when's this equal to 0? Again, when lambda equals -2 or when lambda equals 4. Right? But again, -2 is a repeated one. But you see how there's only 2 distinct eigenvalues, right? Only 2 distinct eigenvalues. Now that doesn't mean, again, that it's not diagonalizable. It might be. All right, but it's not guaranteed though, right? If there were 3 different ones, then I would say, yeah, for sure, A is diagonalizable. But there's only 2 distinct eigenvalues, so I got to check, right? And I got to check the repeat ones, right? This is a repeat solution. Right? This is only a solution once, 4, right? Lambda equals 4. That has an algebraic multiplicity of 1. So you're going to get 1 eigenvector out of this, no problem. All right, I'll do that later. If we can get 2 out of this one, right? This has an algebraic multiplicity of 2. There are 2 factors that this makes 0. So hopefully I can get 2 independent vectors out of this, right? Hopefully its eigenspace has a dimension of 2, and then we can say, cool, we can keep going. And it will be diagonalizable. All right. So I'm going to do that first. All right. So for lambda equals -2, we'll try to find some eigenvectors. Right. I'll start with the repeat solutions. So I'm trying to solve, a minus lambda I times x equals the 0 vector. All right. So a plus 2i, right, is the matrix I'm focusing on. Right. Again, times x equals a 0 vector, but imagine all that's there. So a plus 2i. So I'm adding 2 to the main diagonal entries. So 3, 3, and 1. Oh, I'm sorry, 0. Wow. 1 plus 2, 1 plus 2, and then -2 plus 2 is 0. Okay. 3, 3, 0, and then I've got 3, 0, 0, 0, 0, and 3. Right. All the stuff off the main diagonal stays the same. Now, putting this into reduced row echelon form is incredibly simple. I don't need to go to the calculator for this one. If I just take the opposite of the first row, add it to the second row, I'm getting another row of zeros. So I got 2 rows of zeros here, and then I would, to get it in reduced echelon form, and multiply the top row by a third. 1, 1, 0. And again, you're imagining the equal 0 on the other side. Pivots, the first column is a pivot, so that, what I would call x1 is a basic variable, but then both x2 and x3 are free. So you see, right now I'm seeing that the eigenspace for this eigenvalue will have a dimension of 2. It'll have a basis with 2 independent eigenvectors. So A will be diagonalizable because I'm going to find 2 independent eigenvectors from this one, from -2, and then I'm going to find 1 eigenvector from this one, and that'll make my 3 independent eigenvectors. So here's a matrix. Here's an example of a matrix that has a repeated eigenvalue that is diagonalizable. All right, and we'll get to that coming up. All right. So I'm going to let x2 say be s and x3 be t, right? Because again, they're different variables. Assign them different parameters. From this first one, we're seeing that x1 plus just x2. So x1 plus s equals 0. So x1 equals -s. All right. So I'll actually take the time to write this one out. So the solutions to my equation, the a plus 2i times x equals 0, would look like this. I'd replace my vectors x with, -s for x1, s for x2, t for x3, and I can spread these out, right? There's 2 free variables, so I can write this as a linear combination of 2 vectors, one involving s, right? This would be s times -1, 1, 0, right? Just using the coefficients of s down this vector here, plus, and then one's involving t, and the coefficients of t are, 0, 0, 1. So you see that the eigenspace of A corresponding to lambda equals -2 here is the span of a set of 2 vectors, right? This has a dimension of 2. This eigenvalue has a geometric multiplicity of 2, which is equal to its algebraic multiplicity, and that is wonderful. We want that for every single eigenvalue, right? If every eigenvalue has a geometric multiplicity equal to its algebraic multiplicity, fantastic. Then the matrix is diagonalizable. All right. So I'm going to say this right now. So yes, right? Because I get 2 from here, and again, I'm going to get 1 from when lambda equals 4. There will be 3 independent eigenvectors of A. There will be 3. And again, I got 2 here, but there will be 3 independent eigenvectors of A. So therefore, A is diagonalizable. All right, and let's continue on. So here are a couple, so I'm getting a couple eigenpairs out of this one. So my eigenpairs are, -2 with this one basis vector, -1, 1, 0, and -2, right, still the same eigenvalue, with this other basis vector, 0, 0, 1. Right. So I'm using these when I go to construct my matrix P later. Right. This will be, I'll make this the first column of P, and I'll make this the second column of P. Right. All right. Then the other eigenvalue was 4. Right. -2 and 4. So doing the same stuff. All right. So for lambda equals 4, right, we're looking at the matrix A minus 4i. Right. A minus lambda I. So subtracting 4 down the main diagonal entries, 1 minus 4, -3, 1 minus 4, -3, -2 minus 4, -6, and then all the other ones are the same. 3, 0, 0, 3, 0, 0. Again, pretty easy to do because of all the zeros here. Pretty easy to put this one into reduced row echelon form by hand. Because I can just take the first row, add it to the second row. Second row will be a bunch of zeros. And move any row with a bunch of zeros to the bottom. And then this row with 0, 0, -6 would become the second row. And I'd multiply it by -1, 6 to make it 0, 0, 1, right? Because I want the lead non-zero entry in any row to be a 1. And, zeros will stay 0. I would just multiply that first row by -1/3. So I'd have 1, -1, and 0. Okay, to get, again, the lead non-zero entry, that pivot position to be a 1. So my pivots, again, you can do this with a calculator if you wish, if you couldn't follow along. So pivot there, right? So x2, right, the second variable in my vector is a free variable. I'm going to let x2 be t. Now from this row, we're seeing that x3 must always be 0. Right? Again, imagine the equal 0 on the other side here. From the first row, I'm seeing that x1 minus t minus x2 must be equal to 0, so x1 must also be t, right? Just adding t to both sides. So I have t times 1, t times 0, t times 1, 1, 0, 1 is a basis vector for the eigenspace here, right? So the eigenspace of A corresponding to lambda equals 4 is the span of the set with the vector 1, I'm sorry, not 1, 0, 1, 1, 1, 0, because x1, x2, x3, t times 1, t times 1, t times 0, 1, 1, 0. Good lesson there. Pay attention to the order of your variables, right? So yeah, first component t, second component t, third component's always 0. So yeah, so any non-zero multiple of this is an eigenvector, but again, I can use that. And there's my third independent eigenvector that's going to help me make matrix P. All right, so the eigenpair I'm doing here is 4 with the eigenvector 1, 1, 0, right? That basis eigenvector. And I keep doing that. Keep trying braces, and I should be drawing parentheses. All right, so now let's finish, and I'll just use the calculator to demonstrate. But now I have these three eigenvectors, these three eigenpairs. All right, they're right here. This vector with the value -2, this vector, which is independent of that one, right, with the value -2 as well. Because there were two basis vectors for that eigenspace, and then the vector 1, 1, 0 with the eigenvalue of 4. All right, and again, it doesn't matter what order you put them in, but what order you put them in will dictate what order the values come in down the main diagonal of your diagonal matrix. So now when I go to actually diagonalize matrix A, right, we're constructing this matrix P. It's going to be a 3 by 3 where, again, I'll just put them in the order that I wrote them earlier. So first one, -1, 1, 0. Right? One eigenvector. And then another eigenvector independent of that, corresponding to the same eigenvalue was 0, 0, 1. So I'll make that the second column, 0, 0, 1. And then the third one we found was 1, 1, 0, right, corresponding to 4. 1, 1, 0. All right, this matrix should diagonalize matrix A, right? This is going to diagonalize matrix A into a diagonal matrix D. Now, how do we find this D here? Again, you find P inverse times A times P. All right, and I'll punch these into the calculator. All right, so I'm going to pause it right now and just enter these into my calculator and show you the final result. Okay, so I've done this already. I've entered, on the calculator again. This was called matrix B, and I did B inverse, and this was matrix A, and B inverse times A times B. And you see the diagonal matrix coming up with -2, -2, and 4 in that order, coming down the main diagonal. Right, zeros everywhere else. It is a diagonal matrix. Okay. Wonderful. All right. And like I said, if you were to just change the order of these columns in P, you would just change the order that these values came in. Right. So if I put 1, 1, 0 in the middle, then 4 would be in the second row, second column instead, and -2 would be in the third row, third column. All right. And again, back to the very beginning of the video, talking about the properties of similar matrices. Right. Remember this matrix A and this matrix D are considered, they're by definition similar matrices, so they should have the same determinant. All right, so the determinant of this matrix is just 16. You can go ahead and check up here. The determinant of this matrix would also be 16. All right, they have the same eigenvalues. Clearly, we saw that already. All right, -2, -2, and 4. They have the same rank, right? So they both have a rank of 3, right? This has 3 columns that would have pivots in it. If you were to, well, first off, this is in echelon form. Every diagonal matrix is in echelon form, unless you have 0 down the main diagonal. Then you move your 0 rows down to the bottom. But every diagonal matrix where all the entries on the main diagonal are non-zero is an echelon form, and there's the pivots. Every column's a pivot column, so they both have a rank of 3 and nullity of 0. If you remember nullity, yeah, lots of stuff going on with the they're both invertible, right? Remember, two similar matrices are either both invertible or both non-invertible, and that depends on the determinants, and the determinants are both 16. Lots of stuff you can say now about this matrix and the matrix I started with. And again, what I'm going to get into in the next video is more properties, especially that one about raising diagonals to powers, right? Because raising this matrix to a power will be much easier, right, than raising this matrix to a power, right? Multiplying this by itself 20 times is way harder than multiplying this by itself 20 times. Because when I raise this to the 20th power, I just put the 20th power on each of the main diagonal entries and I've got it. Alright, it's that simple. So I'm going to do that in the next video when I go over properties of diagonal matrices and why the interest in taking a square matrix and kind of converting it into a similar diagonal matrix. Alright, so again, pretty long one today, right? Lots of examples. Hopefully, you saw a lot of the same stuff though, right? You're finding eigenvalues and eigenvectors corresponding to those eigenvalues. But yeah, so you take a square matrix, find its eigenvalues. If it's an n by n square matrix and you find that it has n different eigenvalues, you know right away it's going to be diagonalizable. All right, then you go and find eigenvectors corresponding to each of the different eigenvalues, and put those eigenvectors in as columns of this matrix P that diagonalizes A. If the eigenvalues aren't all different, right, if there are some repeated ones, first take a note as to how many times it repeats, right? That's the algebraic multiplicity. Then for those repeating eigenvalues, find the eigenvectors for those. If the dimension of the eigenspaces for those is the same as the algebraic multiplicity, right? If the geometric multiplicity for those is equal to the algebraic multiplicity, then and that happens for all the repeated eigenvalues, then it will be diagonalizable. Right? If every eigenvalue has a geometric multiplicity equal to its algebraic multiplicity, then the matrix will be diagonalizable. If you find just one eigenvalue with a geometric multiplicity less than the algebraic multiplicity, then it won't be diagonalizable, like in the one example earlier where the eigenvalue of 1 had an algebraic multiplicity of 2 but a geometric multiplicity of 1. Right. All right. So hopefully you have a good time practicing this stuff, problems related to this, similar to this, and thank you very much for watching.